Welcome to the Resairchia YouTube channel. My name is Jorge, and in this video I will introduce you to the CUDA package in Julia and how to use it to model the boundary layer on a flat plate. I was reading how to use arrays in Modia when I saw this example, and it gave me the idea that maybe I could use those arrays and the CUDA package in Julia together. For doing so, I will start by telling Julia that I need to use the Modia, plots and CUDA packages. Then I will run a test based on the example that you can find in Modia's documentation. When we simulate this very short model, we get this collection of values in arrays, and when I plot all of them, we get this plot. So based in this model, I'll see if I can add some CUDA functions and plot the boundary layer results on a flat plate. I will continue now by creating a parallel function. The function will have as arguments 2 arrays and 2 scalar values. I is our index. The threads we create in CUDA, they are stored in something called blocks, and we need to keep track of them based on the block ID, the dimension of the block, and the ID of the thread. I'm not going to explain this better than NVIDIA's documentation, so I strongly recommend you to stop here and read about it if you are not sure of what we are doing. We will have then a big array, capital F, where we will get the results of another function called delta that I will define now. I define now the number of threads and number of blocks that I will use for testing these functions. I will only use 3 threads and 1 block to keep it simple. Next, I define the capital F array using CUDA.fill. I initialize it with zeros so I know what's in there. Next, I define the array X using QArray. It will have a linear range from 0 to 1 and a number of positions based on the number of threads times the number of blocks. So in this case our positions are 0, 0.5 and 1. Next, I define the function delta. The arguments are X, the local position, uinf, which is the way that we usually call the velocity of the flow, and then inside the function I define the Reynolds number, which is the density times the velocity times the local position divided by the viscosity. You can Google or search for the Reynolds number and see what it means, but it's basically a ratio between the velocity and the viscosity. And then we compare if the Reynolds number is above 500,000, we return some value, otherwise we return another value. This function is just for checking for the moment. I will improve it later on. I give a value for our u infinity, in this case 2, and then I call the parallel function using all the arrays and values that we have just defined. You need to use it with add CUDA to tell Julia that we will call a CUDA function, and as you see we use the number of blocks that we defined, the number of threads that we have defined, and the name of our function with all our arguments. And now I show F, which is the results of our function. So far so good. Now I increase the number of threads, I keep the number of blocks as 1 just to keep it simple, and I define the delta function inside another function called flat plate. This is probably not the most optimum way of doing it, but I want to keep things simple. If you look at the delta function, I return a value when the Reynolds number is beyond 500,000, This is the value of the boundary layer thickness when we are in turbulent flow, and below that value we are in laminar flow, giving this thickness. This is just an example. We don't have any model for the transition from laminar to turbulent. That is a very difficult topic, and in this case I'm just trying to show an example. Now I define my Modia model. It is a bit different from before. What I do is I give an acceleration of 100 meters per second, a velocity starting from 0, and then my equations are the derivative of the velocity equals to the acceleration, and thickness is going to be the boundary layer thickness at different points and velocities. And for obtaining that result, I call our flat plate function using the velocity of the free stream at each moment in time. I find very cool that Modia handles these results and creates a simple variable or a big array for us. Next, I instantiate the model and simulate it. Here you can see how the velocity changes from 0 to 200. As we have seen in previous videos, I need to import Modia's results to obtain all the thicknesses. For doing so, we use import Modia result and get plot signal. I will leave a link in the description to a previous video showing how to use the Modia results. Well, as you can see, we got a lot of results. These inf values at the beginning, they come from values at 0. Let's try to plot this to see what happens when we accelerate. At Reynolds numbers very small, very close to 0, the viscous effects are important. So we obtain this very thick boundary layer. But let's say this is a special case for very low speeds. When we start accelerating, you see how the boundary layer is smaller, and you can see how we have a jump in the thickness at the points where we transition. And again, since we don't have a model of the transition, we can see this odd looking jump. But as you can see, the faster our flow goes, the smaller the laminar boundary layer becomes. Thank you so much for watching, and see you in future videos.